No. Okay, so let's begin. So good morning, good afternoon, and good evening, everyone, depending on where you are. My name is Anastasios Panayotelis, and I hope everyone has enjoyed the 2021 International Symposium on Forecasting. I'll be your chair for this final keynote session. As a reminder to everyone, after this keynote, we will have a closing session where, after some brief housekeeping and announcements, we will have a chance to casually catch up with one another, hopefully with a time zone appropriate beverage in hand. So now to introduce our speaker. Biannually, we designate one keynote speaker at the ISF as the Clive Granger Memorial Speaker in recognition of Clive Granger's substantial contributions to our field. And what could be more fitting than a keynote speaker who was influenced by and collaborated with Clive Granger? I speak, of course, of Professor Sir David Hendry. Professor Hendry is a co-director of climate econometrics and senior research fellow of Nuffield College. He is renowned for a distinguished career and for his discoveries in time series econometrics, the econometrics of demand for money, the theory of forecasting, and automated model building, amongst other fields. More recently, he studied the econometrics of climate change, which will be one of the topics covered in his keynote today. The list of Professor Hendry's honours is a long one. He is an honorary vice president and past president of the Royal Economic Society. He is a fellow of the British Academy, the Royal Society of Edinburgh, the Econometric Society, the Academy of Social Sciences, the Journal of Econometrics, and Econometric Reviews. He is a founding fellow of the International Association for Applied Econometrics. He is a foreign honorary member of the American Economic Association and the American Academy of Arts and Sciences. He has received 8 honorary doctorates, a Lifetime Achievement Award from the Economic Social Research Council, and the Guy Medal in Bronze from the Royal Statistical Society. He was knighted in 2009. Last but not least, Professor Hendry is an honorary fellow of our very own International Institute of Forecasters. We will handle questions in the same way as for the other keynotes. In particular, please place questions in the Q&A box and not in the chat, and I will read those out. While I'm reading your question, George will configure Zoom so that you can unmute yourself and have some back and forth with our speaker, should you choose to do so. Alternatively, you may use the raise hand function to ask your question in person as well. It is therefore my great pleasure to now hand the virtual floor over to Professor David Hendry, who will give what promises to be a very interesting and topical talk on forecasting climate change, pandemics, and economics.
Many thanks for that kind introduction. Is this all clear?
Yep.
Yep, very good. So it's a real pleasure to deliver the 2021 ISF Clive Granger Memorial Keynote Address, because Clive was a brilliantly innovative individual. We knew each other pretty well from the mid-1970s, but actually our views only converged about a decade later, as I've spelt out elsewhere. Clive greatly influenced the theory and practice of econometric modelling and forecasting. Although he mainly forecast and focused on economics and finance, he also tackled environmental issues like Amazon deforestation, degradation of fisheries, and historical wheat prices. With more than 160,000 citations and several hundred publications, go check them out. I'm not going to run through them. Though I am unaware of any publications by Clive on climate change or pandemics directly, but were he still alive, his eclectic interests would surely have led him to study these in the current crises that we face. So here's a route map. Now, in part, the route map is guided by the pictures you see at the top. There is all the atmosphere that the Earth has, this thin band, no thicker than a sheet of paper around a soccer ball. This is all the water on the planet, and the oceans, the ice sheets, the rivers, the lakes, etc. That's all the fresh water, and you probably can't see it. That's all the drinking water. Can we pollute that? Can we raise its temperature? Can we fill it with plastic? Of course we can. Can we fill this with CO2? Of course we can. And the net result is the huge changes in temperature that we're witnessing across the planet. So I'll look at forecasting changing climate relationships, forecasting changing pandemic impacts, economic relationships, diverge very briefly to look at the paradox of UK rising real incomes, which I see when I'm modeling climate, yet stagnant productivity, which I see when I'm modeling economics, and try to reconcile them. Then I'll briefly comment on forecasting scenarios and policy. So climate change affects pandemics, which badly impact on economic activity, which in turn is the source of climate change. And that's what motivates my look at the interactions between the three of them. They're certainly measured at vastly different data frequencies, 1,000-year intervals for much of paleoclimate, through annual, monthly to daily for current climate, monthly, quarterly, and annual for economics, and down to daily for pandemic and seconds or even nanoseconds in finance. But there's commonalities to the three different disciplines. They're all subject to non-stationarities, both from evolving stochastic trends and sudden distributional shifts. And they're also subject to major data revisions and changes in data measurement systems. All three face imperfect and incomplete knowledge of their data generation processes because it involves human behavior, and we're a pretty mobile lot. So you have to search for reasonable approximations, therefore they all need model selection techniques. And they need forecasts of likely future outcomes to plan and adapt as events unfold, albeit over very different horizons. Given such commonalities, how are they going to make their forecasts? Well, one way to try and unravel this is to look at the common taxonomy of in-sample problems that lead to forecast errors. So there are three components of observational data models: unobservables, like the error term, observed stochastic variables that you model and model by, and deterministic terms, constant, trends, seasonals, and dummies for outliers, etc. And each component can have one of three mistakes: estimation uncertainty, misspecification, and parameter change. So the taxonomy table of 9 interacting issues highlights the problems that matter and those that are less crucial, although all of them obviously affect how accurate our forecasts are. So if we do this in a 3x3 table, where B denotes a biased forecast and V a forecast error variance, each conditional and all the other components being absent. So for example, when we look at the B here, we don't have either of these, or these. So the main cause of bias in unobserved terms is when you're trying to estimate a forecast origin and get it wrong. If you start your forecast in the wrong place, it stays in the wrong place. But even if you start in the right place, there'll be a variance component from it, from the error terms, and so on. Misspecification of unobserved terms, the main ones being omitted variables, mismeasured in-sample data, unmodeled nonlinearity, and incorrect exogeneity. All of these actually mainly lead to variance components because all the others, remember, are being absent. And finally, changes in the errors lead to variance, heteroscedasticity, and other components. For the stochastic variables, we just have variance components, and this often puzzles people who think that leaving out relevant stochastic variables leads to biases in their parameters. But actually, that's only because of the deterministic terms. And if they're absent, you just get variance components. And then the deterministic terms, estimating them certainly leads to variance. Misspecifying them can lead to very badly biased estimates. Leave a constant out of a model that desperately needs one, and you'll get very badly biased forecasts. And likewise, change in deterministic terms, location shifts, trend changes, etc. So if we have an accurate forecast origin, so that B goes, and we remove in-sample location shifts, so that B goes, then the only B that remains are the ones we can't control, namely forecast period changes. So 3C remains, and if 3C persists, we get what we've long called forecast failure. So let's look at this. Starting with climate. Here are 800,000 years of changes in CO2 over 8 ice ages. They go up and down by about 25 parts per million. But that's big enough to drive the coming and going of ice ages in combination with the changes in temperature. what do we have now? Woof. We're up at 110 parts per million more in 250 years. This massive change is what's causing the climate crisis. If we look at the pandemic, I'm going to focus mainly in the UK for the pandemic, in fact, for all the time series we look at, you can see there's sudden accelerations, drop-offs, flattening, sudden rises, collapses, huge rises, huge falls, and even negative numbers in the British data, which you have to have a method that can handle. What about economics? Well, the Great Recession now doesn't look so great. This is the biggest fall in several hundred years from the lockdown responses to the pandemic, which has led to very big drops. And then something I'll come back to later, the log of UK productivity from 1860, where the trend line has changed many times. There have been very big falls. That's the end of the First World War and the Great Recession in Britain, the interwar period, the collapse at the end of the Second World War, very different changes, trends over the time. And recently, this incredible and previously unprecedented flattening, together with the big collapse, what we call stagnant productivity. I'll come back and say it's not quite as stagnant as it looks. So how do we forecast? Well, most disciplines have what they call structural or theory-based formulations, which are really important for understanding what's going on, but actually in practice often have indifferent to poor forecasting records. Because the key forecasting problem is ignoring location shifts when models are equilibrium correction mechanisms. And that's actually almost all models of observational data. Almost all of them have an equilibrium, ARs, VARs, DSGEs, equilibrium correction models, ARCH, GARCH, stochastic volatility. They're all members of this class, and they all converge back to their built-in equilibrium, even if that's completely irrelevant after a location shift. And the result is then systematic forecast failure. So just as Euclidean geometry is only valid on a plane, although most kids leave school without realizing that, conditional expectations, despite what's said in many elementary statistics textbooks, are unbiased and minimum variance only if distributions do not shift. And they're neither if they do shift. And that also means that the law of iterated expectations then also fails intertemporally. Some models like DSGEs built using it are in fact non-structural and fall apart every time we get major distributional shifts. And that's why we often have indifferent to poor forecasting records from structural models, because they're not picking up all these key location shifts and trend breaks. They're too theoretical. So there are two solutions to systematic forecast failure after shifts. One is to adapt to theory-based systems, and the other is to use robust statistical predictors. And handling location shifts in all three disciplines' models of observational time series improves their forecasts, and that reveals the generality of some forecasting methods. Other generally helpful forecasting practices that Jenny Castle, Jürgen Durnick, and I spelled out recently in forecasting. Sorry for publishing a rival journal, but we like to help new journals come along. Dampen estimated trends and growth rates. Average across forecasts from non-poisonous methods. Well, Clive was a key player in averaging, combining a forecast. It's difficult to know exactly what methods are poisonous, but sometimes it's quite easy. If you leave a constant out of a model, it's not a good one to include in your forecast in general. Include forecasts from robust devices in that average. Select conditioning variables at a loose significance, as we showed last week in a paper that's just appeared in Econometrics. Update estimates as data arrive, very widespread practice, but especially after forecast failure because of parameter and collinearity changes, and shrink estimates of autoregressive parameters in small samples, something we don't see happening terribly often. But people are often fitting models to a small sample of recent data and take the estimated autoregressive parameter as it is, rather than shrinking it. Another forecasting practice that's very helpful is read Clive's publications. They're very valuable when forecasting. And more helpful forecasting practices, Adapt your predictor choice to the data frequency, as I'll show below, and whether it's univariate or multivariate. Address special features like seasonality. That turns out to be very important in explaining differences in forecast accuracy in the pandemic from the different institutions that forecast. Retain theory models as the null when selecting. You don't have to select over variables in a theory model. If they don't matter, they'll get eliminated in the process of selecting over variables that do matter. Apply saturation estimators for in-sample outliers and shifts, as I'll illustrate later. And if you are going to difference the data to fit your model, check that the model's of any use by computing the accumulation of that to get the levels forecast, as often they're very different. And most of these were implied in recent papers by Jenny, Jürgen, and myself. So let's look at forecasting changing climate relationships. As most of you probably know, atmospheric CO2 is increasing at an accelerating rate. As you can see, these are the annual changes in CO2 in parts per million, and yet the trend line is going up through them. This is leading to very rapid rises in Arctic temperatures and steady rises in global temperatures. Ocean heat content has risen dramatically since the 1980s, down to 700 meters, and even more down to 2000. And people often say, oh, but the massive lockdowns worldwide have led to big drops in global CO2. And these are the daily global CO2 reductions relative to a year earlier. And yes, there are big falls, but these are in megatons, and these are in parts per million. And 1 part per million is 8 gigatons of CO2. So this fall would not even be noticed, excuse me, on that graph. Global sea levels rising. You can see it rising at a rising rate if you draw trends through in typical ocular econometrics, much faster than it used to, and that's still accelerating. So I'm going to discuss the annual forecast we have for UK's CO2 emissions from a vector to regression, a classic forecasting model, one that does very well in this situation, providing you pick up the location shifts in sample. I'll then look at a simultaneous equation system of atmospheric CO2. What you say? Simultaneous equation system still in use? The answer is yes. If you've got 800,000 years of data and you want to forecast 100,000 years into the future, and you've got variables like atmospheric CO2, Antarctic ice volume, and temperature, driven by Earth's orbital variations, which are super strongly exogenous, you want a simultaneous equation system. And we can compare such outcomes to those if anthropogenic greenhouse gas emissions continue or even accelerate. So this is the data on UK CO2 emissions. If anyone knows of an even more non-stationary time series than the CO2 emissions in tons per capita in the UK from 1860 to 2017, I'd love to see it. But it's violently non-stationary with a rising trend, huge oscillations in the interwar period, rising back up to the mid-70s before Thatcher tried to destroy the coal industry, and then dropping off radically. If you look at the fossil fuels that drive that, coal rose steadily until the start of the First World War, oscillates again in the interwar period, rises to the late 60s, and then it plunges, and it's now down essentially zero. Oil rises rapidly until the oil crisis, drops off, and it's been falling since. Natural gas explodes, so to speak, after we discover it's all over the North Sea and very cheap to take ashore. And then this is what's happening to the UK's renewables. Now, it may seem odd that all of them are dropping quite a bit, but the reason for that is there's a huge increase in the efficiency of energy use. So the ratio of CO2 emissions to capital stock in Britain, and in the US, by the way, has fallen by 92% over the period from 1860. On the other hand, the US has still got very much higher, if sort of similar trajectory for tons per capita of CO2 emissions per annum. It's up at about 13 to 15 still, isn't quite the latest data, rather than 5, although there are other factors like, do you import your CO2 and send it abroad? Now, what are the distributional shifts? Well, these are the distributions over 40-year intervals. And that's the 19th century. This is the start of the 20th century up to Second World War, continues on through up to 1979, and then it drops very sharply back. So there's very big shifts in the distribution, and that is the mean of the process that you're modeling. So you have to model the mean shift somehow. So we'll model the evolving dynamic relation of UK's CO2 emissions by coal, oil, log GDP, and log capital, but allowing for shifts in the relationship. And I've dropped the slides in that as they're published and a bit complicated, but what I want to focus on are the multi-step system forecasts. They're forecasts in the sense that the data were not used in either model selection or estimation, but they're obviously in the past rather than in the future, although we do show what happens if you go into the future, which is highly dependent on policy. The multi-step forecast from a model that modeled the shifts in sample using step indicator saturation and picked up the Climate Change Act and the European Directive in Renewables, it's got a root mean square forecast error of 29. And you can see that in this graph. And these are the fan charts a la Bank of England around that, going out to 95%. Emissions are the red line, and you can see it's a pretty good description, even if it doesn't get down quite at the end. The blue and the bars is if you use the same system, but you don't model the step changes. And although the latest step change happens back here, 2008, it still has enough of an impact that the forecasts are pretty dreadful. They've got huge uncertainty bands and a root mean square forecast error more than 3 times what you would get if you had modeled the shifts. And later I'll use card forecasts during the pandemic. If we apply it to this kind of data, it's quite good, not great. Root mean squared error of 37, but certainly better than not modeling the shifts that have occurred. So onto ice ages. The discovery, understanding, and measurement of ice ages was really a major intellectual achievement, and the data were an arduous effort. Although everybody now knows what ice ages look like, it really was a massive amount of intellectual energy to discover them and model them. Jenny and I have summarized it in our Foundations and Trends in Econometrics article in 2020, where we modeled Antarctic ice and temperature and atmospheric CO2 jointly in a dynamic simultaneous equation system as interacting functions of super strong exogenous orbital variables. They're super strong and exogenous simply because nothing that we do to our atmosphere affects its eccentricity, obliquity, and precession. Although if we had a nuclear war, we might change that. Anyway, for data up to 100,000 years ago, and then we forecast the remainder of the observed data to test the model, and then we forecast 100,000 years into the future, because of course, these key variables are known for almost certainty that far ahead. The data that we use are measured at 1,000-year intervals in the x-axis, and they're labeled by time before the present, which is denoted by 0, from 800,000 years ago. So these are the orbital drivers. This is eccentricity. You can see it's varied hugely over time. Okay, it's only 5 degrees from circularity, but even so, that's easily enough to drive the ice ages we now know. And there was a quiescent period here, then a lot variation again. And we're going through quite a quiescent period, and it will get more quiescent for a period quite close to circularity over the next 50,000 years or so. Obliquity, you can see that's trended. There's been definite changes in the distribution. Precession, it all looks the same until you look closely. Then you can see big white space, big white spaces here and here, but very close together here and here. So that's also varying. And then that can be computed out. Lankovich did to calculate summertime insolation, but I'll use the 3 driver variables. And what happens? Well, these are the measures of ice ages over the ice volume in Antarctica. This is atmospheric CO2 measured from various sources of what's stored in rocks and fossils, etc. And this is Antarctic temperature, which you can see there was a very big shift about 450,000 years ago to a much more violent oscillation. And you can see this in the 3D plot, that there's a lot of changing relationships between CO2 temperature and ice volume. Nevertheless, over the ice ages, I've calculated the negative of ice volume. So we get the correlations all positive, and you can see they're all extremely high. And that's not a surprise, because if temperature is driving changes in ice, and that then leads to changes in CO2, this is what you would expect. So the model then lets us calculate 100 steps ahead forecasts with error bands taking account of parameter uncertainty and error uncertainty, but not dealing with any of the outliers that we picked up over the sample period. And that's from 100,000 years ago up to now, which is why it's forecasts in quotation marks. And as you can see, the model tracks the data pretty well up until somewhere around 20,000 years ago, when ice volume plunges and ends up outside our 95% confidence bands. Similarly for CO2, we track it reasonably well, obviously much smoother than the actual measures, until about 20,000 years ago, and off it shoots. And for temperature, same story, 20,000 years ago, off it shoots. So something's happening near modern times. Now, Ruderman puts forward the hypothesis that humanity began to influence climate 10,000 years ago by domesticating animals and starting farming. But Snur et al. In 2015 provided evidence of the origins of cultivation long before Neolithic farming. And they date such events to around 23,000 years ago from the presence of proto-weeds. That is, plants will become weeds when we want to grow other things in the area, but they need ground disturbance to grow in new areas, and they show that that was happening. Now, since we know the Earth's orbital path far into the future, we can simulate or forecast, if you like, what would happen if there's no human intervention, continued anthropogenic emissions at 400 parts per million, roughly where we are now, or even if you go to business as usual, RCP 8.5 at about 560 parts per million. Now, the impact of CO2 on temperature is actually log linear. The model's linear, but we work out correctly how to pick out from the log linear relationships ones that match the in-sample period, and then we can start forecast 10,000 years ago. So this is what happens if we use the model and we don't exogenize CO2. So this has got 3 forecasts. That for ice, which you can see looks kind of like the Ice Age period. This only goes back 400,000 years so that we can see what's happening in the future more clearly. Then CO2, and then temperature. And they're sort of like an attenuated version because other things are going on. The dynamics, of course, don't work out when you go 100,000 years ahead. But you can already see that's not correct. That cannot be what's going on because the data lie almost outside where the forecast bands reach in all 3 cases. So I've now dropped CO2, and that's replotted the endogenous CO2 with error bars at plus or minus 2 standard deviations of the forecast error for ice and for temperature. And you can see that they're pretty much what we showed earlier. Now, if I add in the exogenous forecasts, if I exogenize CO2 in the model, so now CO2 is a fixed volume at 400 parts per million, this is what the forecast would look like. Now, they're not dramatically different. This line here was the lowest ice age volume over the last 800,000 years. And this was the highest ice age temperature over 800,000 years. And they do deviate from that, but not very dramatically. But business as usual would be a disaster. We'd have an almost ice-free Antarctic, according to our model, and we'd boil it. which would be consistent with a rise of 4 to 6 degrees in Earth temperature, which would be fairly disastrous for many areas. Many of you will have seen the heat dome over Northwest America and Canada and how appalling the temperatures have suddenly become there. Now, I want to make one point about the informational value of data and how you judge it. The system involves 3 variables and the orbitals, but I can also model the 3 variables by vector autoregression going back 4 lags. And that leads to equation standard errors of 0.094, 5.03, and 0.755. If I add in the orbitals and remodel, but use much shorter lags, only just 1 lag, I get 0.09, 5.13, 0.71. These are not much better, and this one's actually worse. But when I compute the root mean squared forecast errors from the var4, that's what we get. And those from the model with orbitals are almost 1/3 of this, 50% less than that, and nearly half of that. So the fact that you didn't have much benefit in equation standard errors does not tell you you will not have a huge amount of benefit as you go into forecasting. So be very careful how you interpret what you learn from exogenous variables. Now here they're known and they're strongly exogenous, and this matches what we find in an earlier paper with Gray and Meisen. But it is quite difficult to judge models in sample as to what they will do out of sample. So what about the pandemic impacts? Well, thank you, Johns Hopkins University and its CSSE unit for all the work you've done getting the data available in a form that we can use. So we now forecast about 4 times a week, roughly 7 days ahead most of the time, for 50 countries, 50 US states, 300 England local authorities. Each time we've got 4 models. So there's 3,200 models to be estimated each time, 4 times a week. So key to that is downloading and sorting data and forecasting, all being automated, which Jürgen did and shows on his website. Now, there are many data issues, but we forecast from what is measured, as that is probably what's going to influence policy. So here's the COVID-19 UK data, not much happening until roughly October, November, then off it goes, and it really rockets up and flattens off. Deaths rise very rapidly, flatten off, rise moderately quickly, and then very rapidly before flattening. And that's consistent with the new confirmed cases, smoothed in the dotted line and the actual values, and there's our negative numbers appearing again, and the same for deaths, but very much more erratic. And a lot of that depends on what is reported at different days of the week. Weekly vaccinations have also oscillated fairly much, and you can see that the trends for cumulative vaccination have been increasing, and that's the one hope Britain has for getting out of its current mess. Now, the pandemic's put forecasting methodologies under a spotlight. Everyone wants to know what's going to happen and why. Now, there are many variants of epidemiological SEIR models, susceptible, exposed, infectious, removed, and there are many statistical predictors, autoregressions, theta, card, growth curves, etc. Oops, why it suddenly did that? I must have clicked one of the real nuisance that all these hypertext things, when you happen to click on a reference, it jumps to it. I'd like to suppress that. Anyway, it's a non-stationary process, continually changing trends as you saw, explosive roots in some periods and abrupt shifts in others. Sudden change is a salient feature of the pandemic process, not just the measurement of it, but the process itself. There's location shifts from policy interventions like lockdowns. There's evolving technological advances like greatly increased and more efficient testing and vaccines that have been coming in this year. Rapidly changing trends as behavior and virus infectivity changes. So every aspect of UK cases and death distributions changed over time from the start of the pandemic into this year. It is worse than that. The non-stationarity of the pandemic process interacts with the non-stationarity of the reporting process and the changing seasonal pattern it induces, requiring highly adaptive forecasting methods. So the data is doubly non-stationary, as measurement errors, definitional and testing changes interact with the pandemic process. Changing definitions from sudden inclusion, care home cases, lags in data releases at the weekend generating seasonality, increased infection and antibody testing, previous reporting errors leading to negative cases, and some omitted data suddenly being corrected and added in. So these are our 7-day ahead forecasts of English local authority confirmed cases per 100,000 members of that area. And it highlights the losing battle following Christmas. So this is July last year. This is January. You can see a vast increase in the number of cases, thanks to Christmas allowing a lot of mixing from our incompetent government. And this is what it looks like for our forecast through to the 2nd of July. The density of both new cases and new deaths plotted by 3-month windows shifts around hugely. As you can see over these periods, it's just jumping around. Again, you need either method robust to that or to take account of it. So the CARD-T method decomposes data into a trend, a seasonal and a regular component, and then we forecast the components separately before aggregating. Forecasts from trend and regular are computed using a calibrated average of rho, delta, and theta. Rho estimates a simple autoregressive model with seasonality, forcing a unit root if estimates are close to unity, in which case it switches to first difference model with a dampening mean. Delta estimates the growth rate based on first differences, but damped by removing large values and allowing for seasonality. And theta is a trend halved integrated moving average model, namely a damped trend arbitrarily halved as an intercept correction estimated by moving average model, and the seasonal components extrapolated from the most recent estimates. We then compute the arithmetic average of these 3 forecasts and then calibrate it by treating the forecasts as if they were observed. Then a richer autoregressive model is estimated from the extended data series, and the fitted values from this calibrated model are the final forecasts once you've undone any transformations such as logs and differencing. This is a modified version of our M4 competition submission, and higher orders of integration, I2 or damped I2, can be handled, and we've published a number of papers on how it works. So a closer look at how it works. There's a number of stages before we even get to the bits I've described, namely the current trend is estimated by taking moving windows of data and saturating each by a linear trend, so there are as many trends as observations initially. Then we select the relevant ones using autometrics, and these selected linear trends are averaged to give the overall flexible trend. The trend and irregular are then separately forecast using CARD, dampening the trend for forecasting, and the seasonal is extrapolated and added to the forecast for the trend and irregular. We then compute 80% uncertainty bands, and then we go back 3 days, 2 days, and 1 day and apply the same procedures, average those to get a separate set of forecasts. And because these are more backward looking than the red line, when the black line lies below the red line, things are getting worse. When it lies above, things are getting better. So it also gives us an indication of shifts. If you're forecasting before a break, as here in Italian total deaths from 6th to 12th of March last year, you can miss very badly for a short period. But CARD-T recovers very quickly, 1 more observation, and it's going back through the correct trend. So we can compare the evolution of our forecast performance with other forecasts, the Los Alamos National Laboratory. And if I show you the central forecasts up to 7 days ahead for confirmed cases and deaths, the root mean squared forecast errors are very similar across the 7 horizons, which is pooled across a large number of observations for confirmed cases, but ours are very much smaller for deaths up until 7 steps ahead. their interval forecasts are pretty good for cases, often quite wild for deaths, and ours are far too small most of the time, occasionally being a bit too large. So that needs improved. If you compare it to the Institute for Health Metrics and Evaluation forecast, we ran into the difficulty that when the definition of death changed, IHME was forecasting a different definition. So although it looks well out, it's actually got the old definition, whereas we're forecasting a new definition. It just adds to the problems of evaluation. Now, what about forecasting changing economic relationships, which many of you will have had to do in the past? You do need to robustify forecasts from equilibrium correction models after shifts to avoid systematic forecast failure, because they will otherwise converge back to the wrong earlier equilibria after location shift or a trend shift. Andrew Martin, as Jenny and I have developed smooth, robust multi-step forecasting methods that re-estimate the equilibrium correction term after shifts. And here's a simple example of where it went very badly wrong for an institutional forecaster and very right for our methods. So these are smooth, robust 5-year ahead forecasts of UK productivity after 2008 and the financial crisis from quarterly data. So an AR1 model with constant and linear trend actually performs extremely well up until 2008. You can see that the trend is pretty good, but the previous trend, if it continued, would have been way up here. The forecasts you get from this model are very similar to those from the Office for Budget Responsibility, whose forecasts fail after 2008, because you can see this is what we call a hedgehog graph. They're always trying to get back to the previous trend, but that trend is gone. Now we robust transform the local mean correction, and this is what we get out of it. They have a mean squared error, root mean squared error of 3.6, and ours is 0.87. Of course, ours is ex post, but it's ex ante data, and it's using exactly the same data as the OBR used. There's another lesson from this paradox of stagnant real wages yet rising real incomes. The log of UK real wages very closely tracks the log of output per worker per year. But the log of wage share has been falling very steadily this century. And one of the reasons for this is that the log of employment has increased very much faster than the log of population. So if you divide GDP by employment, you get a much lower level than if you divide GDP by population. And that explains why we've had rising real incomes but stagnant productivity, which seems to end that paradox. But no, on Monday, the Office of National Statistics heavily revised the numbers for productivity, and this is the new numbers, quite a bit higher towards the end, about a quarter of the difference from what had been there before. So be careful, beware data revisions. So I haven't terribly much to say about forecasting models and policy. It's very original. Forecasts in all 3 disciplines are made from statistical and both types of structural models that either or don't include the relevant policy variables. And the forecasts from all 9, the 3 disciplines and the 3 types of model, automatically entail a need for policy reaction. For example, in climate, it's reduce greenhouse gas emissions, pandemic, develop a vaccine, improve productivity and economics. But structure models in climatology and epidemiology rarely link directly to specific policies. They don't normally have, say, invest in renewable electricity generation, subsidize vaccine research, generate innovation hubs, etc. They're much more at the general level. Integrated assessment models, of course, link climate and economics, and some generalizations of SEI are linked pandemics and economics. And integrated assessment models need to forecast technological progress to evaluate renewable solutions. And almost all macroeconometric models, DSGEs, simultaneous systems, VARs, etc., link directly to policy. But unless they have handled past shifts, be very careful using their advice. The most forecasts of climate change temperature scenarios are conditional on greenhouse gas emissions, and the implied policy is the need to rapidly attain genuine net zero emissions, with indirect implications for how to achieve that, be CCS, carbon capture and storage, renewables. Multi-period unconditional forecasts would require you to forecast future emissions, which in turn are dependent on future policy choices. But for sea level rises, they're already baked in, so highly predictable. All integrated strategies to reach net zero by 2050 must address the huge expansion needed in highly variable renewables-only electricity generation, and therefore its storage, if to supply all electric transportation, buildings, manufacture, and chemicals, plus tackle agriculture and waste. This can be done, but it's obviously extraordinarily difficult and needs urgent action. And Jenny and I submitted our proposal to the UK House of Commons Public Accounts Committee, and it's on their written evidence website. Forecasts of pandemic evolutions from epidemiological and statistical models rarely have direct implications as to how best to control, because the effectiveness in medical and non-pharmaceutical interventions differs greatly across pandemics, e.g. cholera or COVID-19. But these can be linked, as in Andrew Harvey's recent work. Various agent-based models also study the impacts of non-pharmaceutical interventions, and other models link these to economic outcomes, as in recent work by Judith et al. Forecasts from an SEIR often effectively are scenario warnings to make NPIs when no vaccines available. Now, the policy reactions to these, so for example, back in March last year, huge numbers of deaths were forecast, so the government immediately had a lockdown, so we didn't get huge numbers of deaths. So that scenario was invalidated by the policy reaction. But this is not forecast failure. You have to distinguish from when the policy reaction actually invalidates the model, which that reaction did not. It just invalidated that scenario. And robust predictors after shifts need not have policy relevance. A random walk can be the best forecaster, but doesn't really have much policy content. Conversely, model-based policy forecasts can alter economic relationships, as we saw when the UK government introduced its furlough scheme to combat unemployment during COVID-19. So I'll compare forecasts, again, in samples, so to speak, of UK monthly unemployment rate from CARD-T and an econometric model during the initial pandemic, which is this period over here, relative to UK monthly unemployment. So these are 3-month ahead forecasts from CARD-T and an econometric model, both with and without a furlough policy intervention dummy. Now, red shows what actually happened to unemployment. These are the initial forecasts from the econometric model, which you could take as a scenario, saying that if a furlough scheme was not introduced in late March, this is what would have happened to unemployment. This is the model with a furlough scheme, but there's only one observation to estimate it, so it's very inaccurate. The econometric model without the furlough dummy continues to forecast very badly, but when the furlough ends, our forecasts from the furlough dummy pick up quite well. CARD-T works very well initially until the furlough dummy starts to peter out, and then it gets slightly wrong forecasts. We look at the mean absolute errors, and this is typical of what people see in many forecasting contexts. In April, CARD-T was by far the best, as it was in May and June, and in May, both econometric systems are getting worse. But by July, the model with the furlough dummy is best. And in August, the model without the furlough dummy, which was the best one prior to the pandemic, has come back to being the best. These were quite close to the Bank of England unemployment rates forecast in January 2020 for Q1, 3.8 and 3.9 from CARD, but in August 2020, the BOE predicted 7.5% in Q4, we predicted 4.7, and the outturn was 5.1. So it really would have paid the bank to adopt some of our robust forecasting devices. So what conclusions do I draw? Time series forecasting mutters on thanks to people like Clive, a real time series pioneer. He's a rebel without a causal model, and he always argued for causality of a Granger kind, but realized that did not entail causality of the kind you needed, where a vaccine actually causes fewer cases in a pandemic. That's not Granger causality, that's real causality. So what conclusions do I draw? Well, the commonalities across climate, pandemic, and economic observational time series are there because they all interact. Climate change affects pandemics, affect economic activity, which feeds back to climate change. All three face non-stationarities from both stochastic trends and abrupt shift. I haven't talked much about stochastic trends, but they're actually handled in all the cases I've looked at, but it's co-integration and differencing are so well known, they didn't need me to tell you about it. But you still need robust forecasts to plan over different horizons. Incomplete knowledge of the data generation processes in all three entails model search for structural representations. In all cases, we did a lot of search, or if you like, machine learning. Forecasting similarities and differences across the differences, across the disciplines, partly dependent on the data accuracy and its frequency, partly in valid conditioning variables being available, and partly in the extent of non-stationarity. If the processes were all stationary in all the disciplines, any old model would forecast just as you expected it to. It's the non-stationarity that stops that happening. The applications illustrated and compared forecasts in all three areas, and the software is widely available, free in GETS, nearly free in Excel Modeler, and a bit more expensive if you want the whole caboodle in Autometrics. Thank you very much.
Okay, so thank you, Professor Hendry, for an excellent talk. So we'll have the Q&A now. As I said earlier, just type your questions in the Q&A box, not in the chat box. Alternatively, raise your hand and we'll let you in. So I'll begin with the first question, which is from Esther Ruiz. What is the most relevant frequency of observation when trying to forecast climate change and its relation with economic variables?
Yes, Esther, that's an interesting question. I haven't ever tried to optimize what would be the best, because it's a trade-off between the accuracy of the data and the frequency of observation. So quarterly economic data are not terribly good and are often heavily revised. So annual is probably a better bet, but I've just shown you that even something as well established as the productivity time series in the UK was suddenly revised out of the blue on Monday of this week by the Office of National Statistics. And it makes quite a difference if you're going to forecast where productivity will go from there, and consequently, how much climate effect it will have. Now, climate variables are almost certainly better modeled on something like annual, because the seasonal fluctuations are changing all the time. They're different between North and South hemispheres. So you've got quite complicated problems of dealing with the non-annual data. So I would go for annual data if you want to relate climate to economics.
Okay. The thing why I was asking is because there are many studies now trying to relate economics and climate, and many of them are using monthly, quarterly, because with economic data, we are more used to this. And that's why I was asking what was your idea about this. So thank you very much, David.
It's all right, thanks, Esther. We have long annual time series for much of the world for both of these. So you would give up some observations relative to, but it is a trade-off between the accuracy of the higher frequency ones and, of course, the longer lags you need. I mean, a change in something like CO2 on a monthly basis would take quite a while to feed through to affect the economy and vice versa.
Okay, thank you very much, David.
Thanks.
Okay. Are there any, if there's any other questions, please in the Q&A, here comes one. So one from Bachman, Rostami Tabar. What are the conditions under which a forecasting model should be changed or modified, and how often should that be done in practice?
Well, it should certainly be updated every time it misforecasts. And if it systematically misforecasts, I would think you want to change the model. And you could do that in many ways, not necessarily going back to square one, but first of all, looking to see why it's misforecasting and using things like intercept corrections or step indicator saturation.
Okay, I'm just checking if there's any hands up or any more questions. Here comes one from Nikos Kouredzes. So using extra long time series, for example, in climate change, we often take a hit in sampling frequency, but towards the modern times, we have much more sample. Can we reconcile the two?
Well, that's sort of like Esther's question, that yes, high frequency data other than, say, stock markets is often subject to quite a range of measurement errors. And while it may be much longer, you have to deal with those in some sense as to what's going on and the consequent revisions. Now, the key area that's worrying in forecasting are measurement errors at the forecast origin. Because if your forecast origin is a long way from the true state of the economy at that time, or the true state of climate at that time, you'll get serious forecast errors. And one reason for using longer frequency data, like annual, is that that's less likely to happen, although it's still going to happen.
Okay, so it seems that there are no further questions, and that's it's quite timely actually, because we're just about on the hour. So I'd just like to thank Professor Hendry one final time for an interesting and fascinating talk. Thank you very much.